Forecasting is essential to efficiently plan for the future. For example, for the scheduling of stock or personnel. The autoregressive integrated moving average, ARIMA model, and its derivative are some of the most widely used tools for time series forecasting. The ARIMA model is a quantitative forecasting method. It assumes that patterns and trends in the past data will continue into the future. More precisely, it captures the autocorrelations in the data. Nowadays, we can accelerate these workflows with the GPU-accelerated ARIMA implementation available in RapidQML libraries. While some of the work is still in progress, it provides support for seasonal models and already delivers speedups in comparison with stats model, which is a popular solution for Python users. In this demonstration, we will quickly walk you through using RapidQML to compute time series forecasting. The ARIMA model is almost a drop-in replacement for stats models SariMax. We first start with stats models. We have a CSV file that contains the names of the variables on the first row, and on the following rows, a sequence of observations. We want to output forecasts in the same format, computed with an ARIMA model. SariMax takes only a single series, so we need to use for loop. When we use QML, we can simply pass the full dataset to the ARIMA model without using a for loop. There are many implementations of ARIMA, but for Python users, the most relevant one to compute against is the stats module. For the benchmark, we chose a dataset called Web Traffic Time Series Forecasting because it is a large dataset. For simplicities, we are using a single model for the whole batch of series, and we measure the time that it takes to feed the model parameters to the dataset for batch sizes from 1 to 10,000. To measure the forecast accuracy, we use the seasonal mean absolute scale error. This measure is scale invariant, so we can visualize the result over the whole batch with a box plot. QML ARIMA is meant to work with many series simultaneously. It is fast for a large batch of input data. Processing 1,000 series takes only 12 times longer than processing a single series. This is due to our implementation taking advantage of the parallel structure of GPUs to process many time series concurrently. The drawback is that processing a single time series is currently slower than stats model. For a large batch size, such as 10,000, on this dataset, QML is 5 times faster than the go-to solution for Python users running on 40 CPU cores. Some current limitation for QML on time series forecasting is that it lacks support for exogenous regressors and not very robust to missing observations. SHAP is short for Shapley Additive Explanation. It provides a principal way to explain the impact of input variables on each prediction or on the model overall. And this is critical for model interpretabilities. SHAP incorporates ideas from game theory to compute well-justified additive analysis of how each feature contributes to a given prediction. and it can be extended to compute the impact of interacting features as well. However, in many cases, data scientists have avoided SHAP, as it could be computationally expensive, especially if we want to deploy it in large-scale production. Now, with GPU-accelerated SHAP, a single GPU can compute explanations 20 times faster than a 40-core CPU node, and the speedups grow even greater when analyzing interactions. QML SHAP-based explainers accelerate the algorithmic part of SHAP. They are optimized to be used with fast GPU-based models, like those in QML. By creating the datasets and internal calculations, alongside minimizing data copies and transfers, they can accelerate explanations significantly. But they can also be used with CPU-based models, where speedups can still be achieved, but those can be capped by factors like data transfers and the speed of the models. Till now, we learned about the QML machine learning libraries, which is a GPU-accelerated libraries, its functions, and various features that it provides to make the task of data analysts and data scientists easier. It is better than various other machine learning libraries like scikit-learn, which doesn't support GPU directly. QML API is easy to use because QML functions look and feel just like scikit-learn. You initialize them with key parameters, feed them with a feed method, and then call predict or transform for inference. Moreover, we have seen that how it increased the speed of the clusterings and time series forecasting more than 20 times compared to CPU-based machine learning algorithms. Because QML's estimators rely on highly optimized CUDA primitives and algorithms, on a modern GPU, these can far exceed the performance of CPU-based equivalents. To maximize performance, keep in mind, a modern GPU can have over 5,000 cores, so make sure you are providing enough data to keep it busy. In many cases, performance advantages appear as the dataset grows. Overall, we learned the benefits of using the QML libraries and its advantages. Hope you have understood the concept thoroughly. Well, here comes to the end of the topic. Let's try to wrap up here. The big data ecosystem continues to evolve with a lot of choices, like Spark, Dask, Nordic, BigQuery, Snowflake, etc. Historically, many of these options require a trade-off between usabilities, flexibilities, and scale. And empowering data analysts and data scientists to explore and analyze big data seamlessly has tremendous benefit to a business. More insightful BI reporting, more accurate forecasts and predictive models, and more data-driven and innovative decision-making. When used rapidly, it offers a great first step to accelerate the big data workflows due to its easy setup and familiar Python tools, APIs, and interface. Moreover, we can see the performance acceleration for both managing huge datasets with QDF and performing machine learning tasks with QML. We hope you enjoyed the topic and see you in the next topic.